We are continuing with part 3 of the slides, and it deals with the Lagrangian multiplier. Now, the method of Lagrange multipliers can be used to solve constraint optimization problems, such as your production equilibrium problems, but you've also encountered it with consumption equilibrium problems previously. Now, what we have is an objective function. That is this function over here. And an objective function defines the objective of the optimization. So, for example, you may want to maximize your output or minimize cost, etc. And we have a constraint that poses some limit on the optimization. For example, with consumption equilibrium, you dealt with a budget constraint, and you will see for production, you will have a cost constraint. So to optimize an objective function such as this, subject to a constraint, here this Greek letter phi is just a function of these two variables x and y, and it is equal to some constant. So this is our objective function, and that is our constraint. Now, the point is to determine the numbers for x and y. In this case, that will be the optimal solution to the constrained problem. So what point of x and y will be the optimal solution for this particular problem? In our case, we may need to maximize output, or you may be presented with the situation where you need to minimize costs. And then you need to determine what solution of x and y, and in this case, x would represent labor and y would represent capital, that would either maximize output or minimize cost. Now, the steps that must be followed is, firstly, you need to define a new function. And your new function is a function of three variables, x, y, and lambda. So, of course, your x, y would become labor, capital, and lambda. And it is equal to the objective function plus lambda, and then this portion represents the constraint that was set equal to 0. So m is the constant, and you, for instance, if you have cost would be your constant, and then you take all the other variables to the same side as cost, so that you have cost minus the other variables. So that becomes your constraint multiplied by the scalar lambda, that is your Lagrange multiplier, plus the objective function gives you your new function, right? So then you have a function of three variables. The next step is you need to solve simultaneously with these three equations, and you obtain them by getting the partial derivative of your new function, first with respect to x, so in your case with respect to labor, with respect to y, so that would be with respect to capital, and then lastly your final partial derivative of this function with respect to lambda. And then you set them all three equal to 0 so that you can solve simultaneously for your unknowns x and y in particular, right? So in step 1, we are combining the objective function and the constraint into a new function, right? And then secondly, you need to solve simultaneously by setting your first order partial derivatives, of which you would have 3, and set them equal to 0 so that you can solve for your 3 unknowns. We will look at 2 examples. So the first example states that we are going to have to minimize cost, but it is subject to a production constraint. So now, if you have a production constraint, that means you are given the output, and you need to determine what labor and capital should be in order to minimize the cost to produce that given output. So therefore, your objective function now is not going to be the production function. However, your objective function now is your cost constraint, right? So your cost constraint is your objective function, because we want to optimize, we want to minimize cost. So that is the objective function. We need to determine what quantities of L and K is going to minimize cost. And now your constraint is the production constraint of 40. So remember I said the first step is to define a new function. And how do we go about that? Well, first rearrange your constraint. So this is your M essentially, your constant. So remember I said take everything over to the one side such that you have M minus what was on the other side. So if you take this over, it's going to become 40 minus 4L to the power of a half, K to a half. And that is what you see over here. So by defining our new function, there is our constraint in the square brackets, and it is 40 minus 4L to the power of a half, K to a half. Then you multiply it by the scalar, lambda, as we have there. This must be a plus sign. Okay, we won't go into the technicality of that now, but this must be a plus sign. And then your objective function is the 40L plus 10K. So there is your new function. So now you can just go a step further by multiplying out to each term. So that becomes plus 40 lambda, and positive times a negative is going to give you minus 4 lambda all to the power of a half, k to the power of a half. The next step is to get your three first order partial derivatives with respect to this function, with respect to labor and capital and lambda, but treating the others respectively as constant. So this was the function, your new function that you obtained. So your partial derivative now with respect to labor, treating capital and lambda constant, I'm going to differentiate wherever I see L. So therefore, if I differentiate that, I'm just going to get 40. That I treat as a constant, that I treat as a constant. But I have L in this term over here. So I'm going to have to say 0.5 times this coefficient over here, which is minus 4. It's going to give me minus 2. Then I have lambda. I have L to the power of a half, but it's going to be the power of a half minus 1, which is going to be L to the minus a half. So I'm going to put it in my denominator. And then I have K to the power of half still in my numerator. So you could leave it as L to the minus a half, but then it needs to be on the top in the numerator. Okay, and you set that equal to 0. So now I'm going to rearrange this, making lambda the subject of the formula. So by rearranging, you're going to end up getting 20L to the half, K to the half. Next, you're going to get your partial derivative of this function, but with respect to K. So therefore, I treat that as a constant, but if I differentiate that, I'm just going to get 1. The exponent 1 times 10 is 10. K is raised to the power of 1 minus 1. K is raised to the power of 0, so that is just 1. So 10 times 1 is 10. And then that I treat as a constant, but here I have K. So I'm going to bring my exponent down, multiply it by the coefficient 1, times minus 4. It is going to give me minus 2. I still have lambda and L to the power of a half because you have multiplication signs in between all of these, right? Although we don't state it as such. So it's multiplicative, so it's not a case of we treat it as constant and it falls away. It has to be there. So we have 2 lambda L to the half, but now K is raised to the power of minus a half. So you could have K to the power of minus a half next to it, or you could write it in the denominator. So since we've set this equal to 0 as well, we can now rearrange this such that lambda is the subject of the formula because we obviously want to solve simultaneously to determine L and K. So that is what was done over here. And then lastly, your partial derivative with respect to lambda, treating L and K as constant, what you end up with, please remember, you essentially end up with the constraint, right? So if you were to differentiate this, get your partial derivative with respect to lambda, you are going to end up with 40 minus 4L to the power of a half, K to the power of a half, and you set it equal to 0. Now, if I equate these two, right, as I've done here, I can set them equal to each other. You can now solve, and of course, this becomes 20L. Over here, you can add your exponents, so 0.5 plus 0.5 is just L to the power of 1, and you're going to have 5K k, because here you would add your exponents, so you end up having 5k. So therefore, I can rearrange this in the form of 20 divided by 5 is going to give me 4L equal to K. Or you could have it as L is equal to a quarter K. But remember, it is always easier to work with an optimal mix where you're not dealing with fractions. Okay? Right. So remember, we are now using our Lagrangian multiplier. We, in the previous step, if I just go back, we had 4L was equal to K. What do we do with this? Remember, we are solving simultaneously. So I can substitute 4L equal to K into this partial derivative, because here I don't have lambda as I did over here. I only have these two unknowns L and K. And if I substitute 4L, which is equal to K, into this partial derivative, I would be able to solve for one unknown and able to eliminate one unknown step by step. So now if I substitute for K, it was equal to 4L. Now remember, step by step, this 4 is raised to a power of half, and that L is also raised to the power of a half. So you end up having 4 to the power of a half and L to the power of a half. So you end up being able to add the L to a power half. The halves add up to 1. And here you would end up having 4 to the power of a half is 2, and 4 times 2 is 8. So therefore, L is simply going to be equal to 5, 40 divided by 8. And K, which was equal to 4L, it is going to be equal to 4 times 5, and K is equal to 20. Therefore, you can solve for your cost by substituting L is equal to 5 and K is equal to 20 to determine the cost or the minimization of cost that was subject to that production constraint. And C in this case is equal to 400. Now here you have a slightly different example. Here, you are asked to provide for the maximization of output subject to a cost constraint. So in the first example, you had to minimize cost subject to a output constraint, and this is the maximization of output now. So we don't have Q, but it is subject to a cost constraint. So here we have C. So it is important that you read the question carefully. So you're given your production function. Now this is going to be your objective function because we don't have Q, and we have our wage rate, our rental rate, and we have our C, our total input cost. And we need to find the values of K and L that's going to maximize the output of the firm. So first step is to specify that new function. In specifying your new function, this is now your objective function, right? As you can see over there, 2L to the power of a half, K to the power of 0.3. So this is your objective function because we want to maximize output. And your constraint over here is given by your cost constraint. So if you were to first write it as your cost constraint, you would have C, which is equal to 1,280, is equal to WL, so that would be 8L, plus RK, which is going to be plus 12K. And if you rearrange it such that you have M minus your phi, which is a function of those two variables, it would be 1,280 minus 8L minus 12K. Then you multiply it by the scalar lambda, and you add it to your objective function, and you have your new function. The next thing that you need to do is to, of course, solve simultaneously. So therefore, let me just go back. In order to solve simultaneously, you need to get your partial derivatives of that function with respect to labor, capital, and lambda, set them equal to 0, rearrange the first two, making lambda the subject of the formula so that you can equate these two, and you would get K is equal to 0.4L. Then you can substitute this into this partial derivative over here because you would then eliminate another unknown. And then, of course, you can solve for labor, capital, and finally output. So by substituting K is equal to 0.4L into this partial derivative, You can eliminate another unknown and determine labor, and then you can determine capital, and then these two you substitute into your production function to determine output.